All right, so that we're still on Newton's second law, but now that's kind of like getting us into weight and mass. And really, it's so funny because I was just reading something for public schools about this and how this was being taught in like fifth grade or something, and how they were using these two words interchangeably. And then teachers from, farther on grades were like, please don't say that they're the same thing, because they're absolutely not. So I want you guys to know from the get-go that weight and mass are different. And so mass is really sort of how much matter something has. And I always just use the example of, let's say that we were going to go to the moon, okay? So if I'm here on Earth, I have a certain amount of mass, right? Because I'm made up of a certain amount of matter. If I go to the moon, do I still have the same amount of mass? Am I still made up of the same amount of matter? If you say no, then that's incorrect, because I don't change how much matter I have from going from Earth to the moon. Maybe give or take slightly, but for the most part, I'm the same. Now, if I weigh myself on Earth and then I go to the moon and I step on a scale, I am going to weigh differently. I'm going to weigh much less on the moon. Why am I going to weigh less on the moon? You know how people are kind of like floating around on the moon? If you were going to weigh yourself in the water, think about in a swimming pool, how you feel, right? Because of all that buoyancy. And if you were going to put a scale in the water, do you think you would weigh what you weigh? No, because it's a little bit different, right? So same thing with weighing yourself on the moon. It's based on gravity. Okay, so weight is based on gravity. Mass is its own thing. Weight is mass times gravity. Okay, so for example, there is an example in here. Let's see, example 210. It says, what is the weight of a 60 kilogram, and it has 60.0. So I know that doesn't really look like 60, but it is. 60.0 kilogram person on the surface of the Earth. Okay, that's all it gives us. It doesn't tell us any kind of gravity. Should we know what gravity on Earth is? Yes, gravity on Earth is 9.8 meters per second squared. You have to know that. Okay, so we've got mass and we've got gravity. We had to know this. It did not give it in the problem. So weight is equal to mass times gravity. So we've got 60 kilograms times 9.8 meters per second squared. If you multiply that out, you get 590 kilograms times meter per second squared, which, remember, what's that again? That is a Newton. Okay, so it started out giving us 60.0, which is 3 significant figures. Because of this 9.8 meters per second squared, it just makes it into 2 significant figures. So, all right, this next example, it says a 60 kilogram person, so still a 60 kilogram person, weighs 100 newtons on the moon. What is the acceleration of gravity on the moon? Okay, so kilograms is a mass. Newtons means it's talking about a force. It's wanting us to figure out the acceleration of gravity, which is, I'm just going to say, look at these two equations really quick. Do they kind of look the same? They do. Weight is a force, okay? Gravity is an acceleration. So those two equations are kind of the same. So I'm trying to find acceleration here, or gravity. You could say either way. And so I'm kind of rearranging this equation right here. It has 3 variables, so I can put it actually into a triangle. Okay, if I'm trying to find gravity, then that means I have to take weight divided by mass. All right, so my weight here is 100 newtons, and the mass is 60 kilograms. And actually, I'm going to bring it down even more because I want to go ahead and write that a newton is kilograms times meter per second squared divided by 60 kilograms. So what happens is my kilograms cancel. And if you take 100 divided by 60, you get about 1.67-ish, or like 1.6 repeating. So how many significant figures should I have? I've got 3 here and 4 here, so you got to go with the lowest. So 1.67 meters per second squared is your acceleration or your gravity. So that's what the gravity is on the moon. So the gravity on Earth is 9.8. So quite a bit more, right, than the moon. That's why people, when they go to the moon, they jump around like they're kind of like they're in the water almost. Okay, so that is weight. And the last law that you need to know for Newton's laws of motion is Newton's third law. Okay, so Newton's third law, you've probably heard it too. It states, and I don't really like the way that they state it here, because I'm going to say it a little bit differently, the way that you've heard it probably. For every action, there's an equal and opposite reaction. Okay, so every action, there's an equal and opposite reaction. I'm almost positive that you've heard that saying before. So like, for instance, it's showing these 2 football players. If you are playing football and you run into someone and you tackle them, they will have an equal and opposite reaction. So like, you apply force to them, they apply force to you. If your force is more, what's going to happen to them? They're going to go flying backwards, right? Or vice versa. So if I walk on the earth pushes up on me. If the earth pushed up more on me than I push on it, I'm going to go flying in the air. If I push more on the earth than it does on me, I'm going to sink down into the earth. Okay? So there's an equal and an opposite reaction, thankfully. As I'm sitting in my chair right now, there's an equal and opposite reaction, thankfully. Otherwise, I'd either be on the ceiling because the chair is pushing up more on me than I am on it, or I would be down on the ground. So right now, I am pushing the same as the chair is pushing on me. Okay? All right, so I want to stop the video here because I don't want to do a whole, I want to start a whole nother one for momentum. All right, so we're getting close to the end. Unfortunately, this chapter is just a lot of information. So, all right, I'm going to